All right, I'm going to get started. Welcome everyone to this BCI Society BCI Thursdays event. I'm really excited because now we have a slightly new format, and this is based on popular demand from the trainees. And so this is all organized by the BCI Society's postdoc and student committee. And so let me just first introduce myself as Sergey Stavisky. I'm currently a postdoc with Krishna Shenoy and Jamie Henderson at Stanford, although this is actually my last day as a postdoc, and I'll be starting my own lab at UC Davis starting tomorrow. So what's new about this format is we actually now have one academic and one industry speaker, and this reflects sort of a growing neurotech industry in our space and a huge demand by trainees to learn more about those opportunities and see what kind of work they might want to do in the future, either in the academic or industry track. And so today we're going to have two awesome speakers. They are Chethan Pandarinath and Joey O'Doherty. Chethan's at Emory and Georgia Tech, and then Joey is at Neuralink Corporation. And so we're going to have these two half-hour talks where we'll have an opportunity for some Q&A right after each talk. Chethan will speak first and then Joey. And if you have questions, please type them ideally in the Q&A box, which is different than the general chat, although I'll try to read both, and I'll just read those out for the speakers. So without further ado, let me introduce Dr. Pandarinath. He's an assistant professor in the Coulter Department of Biomedical Engineering at Emory University and Georgia Tech. His research uses electrical engineering principles and artificial intelligence methods to study the nervous system and design assistive devices for people with neurological diseases or injuries. During his PhD at Cornell in the EE department, his research focused on the early visual system, and he was trying to create a novel retinal prosthetic in order to restore vision. His postdoc at Stanford with Jamie Henderson and Krishna Shenoy as a part of the BrainGate team focused on improving the performance of brain-machine interfaces to restore function to people with paralysis. Chethan is a Sloan Fellow, and his work has been funded by the Nielsen Foundation, NSF, DARPA, Burroughs Wellcome Fund, Simons Foundation, and NIH. And this next bit is going to sound random, but it will come full circle. As a high school student, Dr. Pandarinath participated in the North Carolina Summer Ventures in Science and Mathematics program at NC Central University. And if you stay tuned, you'll find out why that's really exciting. Chethan, the floor is yours.
Awesome. Thank you very much, Sergey. Give me 1 second to get things going here.
While he's doing that, I'll just say it's a pleasure to have Chethan because he was also a postdoc in the same group I am now, so we actually overlapped.
All right, how are we doing? Can you all see slides here? All right, well,
yep.
Thanks again. Thanks so much, Sergey and the BCI Society for inviting me and for doing this. I think it's really a wonderful idea. It seems like a great potential format. It's the right time to make sure we've got conversations going between academia and industry, and really to expose, I think, trainees to the wonderful work that's going on kind of on both sides of the aisle there. So thanks so much for getting this going. Today I'll be telling you about a general kind of flavor of work we do in my lab, which is this idea of trying to fuse motor neuroscience principles and artificial intelligence to try to create next generation BCIs. So I think as we're all really aware of, it's an exciting time for BCIs. Here I'm just highlighting kind of a few recent successes from kind of the academic side, the amazing work happening at Pittsburgh with robotic control and tactile sensation, Case Western with restoring voluntary limb control through FES. Out at Stanford, where I did my postdoc, we've done some communication work, some of my own point and click typing work, and more recently some amazing rapid typing through decoded handwriting. And there's also so much amazing work going on, including that from the Chang lab going on with speech decoding and synthesizing speech. So it's really just an exciting time in BCIs on the academic side. And then, holy cow, is it an exciting time on the industry side as well, right? So just the number of amazing both BCI and just kind of neurotech industry companies in general is just kind of astounding. And my former advisor, Krishna Shenoy, keeps this growing list, which Sergey pointed me to, about both academic groups and industry, companies that are doing research or work in this space. So, it's a fascinating time. I think the field is really kind of shifting pretty rapidly, and I think the way things have been going, personally, as I do from time to time, I hope we all do, I kind of stop to think, like, what is the role of academia in BCIs? If we've got, these, amazing industry partners and resources and just so much work happening in this space, what do we want to do in academia? And so I'd say kind of a basic premise for my work and my lab is just, there's still a lot to learn about the brain. I think there are a few people that would debate that. And then further, that understanding the brain better can lead to higher performing, more robust, and more practical BCIs. And I think this is really, in my opinion, the sweet spot for academic BCI research. There's lots of ways, we can make progress. There's some ways I think it'd be foolish to try to compete, and there's some ways I think, it's really kind of the right thing to hit. So let me just tell you a little bit about what I mean. So here's what I think kind of a wonderful example of the challenges we face in BCI development, and the ways in which kind of, a better understanding of neuroscience can help alleviate those. So this is now a classic video from 60 Minutes from 2012, highlighting some of the amazing work happening at Pittsburgh from Jen Collinger and Andy Schwartz and Rob Gaunt and others. So I'll just go ahead and play this clip to show some of the challenges their participant was facing. I love this clip because, they were really upfront, both about the performance they were getting, but also kind of the potential challenges they were facing. And that's wonderful, and it's, kind of really honest reporting.
Andy Schwartz believes that will help with some of the things that Jan has trouble with.
Okay.
For example, sometimes when she looks right at an object, she can't grab it.
Okay, I'm going to take the cone away. Just go ahead and close it.
Oh, sure.
So as soon as I take the cone away, there's no problem. But as soon as I put the cone there, she can't do it.
Why is still a mystery.
So that was an example of where, they had trained a decoder to, learn how to grasp what patterns of activity relate to the intention to grasp, and they would use that to grasp with the robot. And then, they found that a simple kind of contextual change caused that decoder to break, right? So here's an example where the relationship between neural activity and behavior kind of learned in one context, it might not generalize to new contexts. And they did some amazing work later where they kind of showed how to get around this problem and how to solve it. I think it's really inspiring to see how, kind of our potentially naive initial approaches or initial thoughts about kind of the relationship between neural activity and movement can lead to problems. But of course, with a more kind of I think rigorous approach where we systematically kind of understand the factors that are influencing neural activity, we can get around those problems and improve BCI performance. So what are the things we kind of think about in my lab? The things we think about are maybe two buzzwords really quick: dynamical systems and machine learning. And I think, combining these things yields a powerful approach for interrogating neural population activity. So what do I mean by that? So if you think about kind of classic single neuron studies, I'm talking about, like, when we think about how the brain controls movement, we often think back to, the pioneers, Everett, Georgopoulos, Schwartz, Kalaska, where they would record from single neurons and relate the activity of those neurons to externally measurable variables like an arm velocity or something like that. And if you can only record from a single neuron, that's, you don't have much choice. You can record something and you can relate it to other things that you measure, but the technology is changing pretty rapidly, as I'm sure we'll hear more about from Joey later. But with large scale neural recordings, we can relate a neuron's activity to other neurons. So we can interrogate patterns that are distributed across the network of neurons, and these patterns are difficult to uncover from single neuron recordings. So what I want to tell you about is just how kind of modern machine learning allows us to precisely uncover patterns from complex and noisy data sets, and how this can be super useful in interrogating the dynamics of, population dynamics in the brain. So here's an example. I'm just going to tell you a little bit about what I mean by dynamical systems. So here's an example of work from Mark Churchland and John Cunningham from Krishna Shenoy's lab, which was published in Nature in 2012. And they trained a monkey to reach with his arm in a lot of different, so these are hand trajectories as the monkey kind of navigated a virtual maze. So, there's some straight, like point-to-point reaches you can see, but if they put barriers in the maze, the monkey would be forced to make curved reaches, and they were able to use this to get a lot of different potential conditions. And so what we see is that if you look at the structure underlying neural activity, so they would take like, a given condition, which might be like a reach down and to the left, and average the recorded patterns that they see across many repeated trials of the same condition. They would get what we'd call a PSCH, which tells you kind of the average response for a given neuron to that condition. And you can use dimensionality reduction techniques to interrogate the patterns underlying the population's activity. And so we get a simple visualization here where each one of these trajectories represents what the neural population is doing for a given condition up here. So for every type of reach the monkey made, there's a trace down here that gives us a summary of what the neural population was doing. And the key thing to point out here is that regardless of the type of movement the monkey was making, the neural population was doing, there were patterns in the neural population activity that were really, really consistent across all these different reaches. And the point is that they didn't necessarily relate, precisely to what the monkey was doing, but rather to relate to kind of the internal computations and dynamics happening in the network. So, obviously in the short format, we don't have time to kind of go into the details of this, but let me just tell you about how, we can make this type of, these types of findings relevant to BCI. So as I mentioned, when they were doing this work, for each of these traces, it represents the average of maybe 20 reaching movements of the same type. That's not great for BCIs. If we need to, do many, many movements in order to pull out this type of structure, well, we don't want a person, when they want to use the BCI, to have to repeat the movement 20 times in order for our BCI to be able to decode it. So instead, some of the techniques that I developed with David Cicillo, my postdoc advisor, Krishna Shenoy and Larry Abbott, and others, relate to using modern machine learning, so recurrent neural networks, to try to uncover these patterns, but to try to uncover them on individual movements. So here's an example where we took the same data that Mark and John were looking at, and we used recurrent neural networks to try to pull out these consistent patterns, but on individual trials. And what we see is that we can now uncover these patterns on individual reaching movements. So what we're seeing here now are, a bunch of traces representing, each trace doesn't represent a condition, but it represents a single attempt of the monkey to reach with its arm. And so we see across 2,100 reaching movements, we see kind of the same structure that they were seeing, but now we see it on individual trials. What can we do with that? Well, what that can do is lead to better decoding performance. So here's an example where we then said, all right, let's try to decode the monkey's behavior. So what I just showed you was, taking the neural activity and trying to find these patterns, but not really knowing anything specifically about what the monkey was doing. And then we said, all right, how well do those patterns relate to the monkey's behavior? So here's that virtual maze I had mentioned where the monkey's making, reaches down and to the right or up and to the left or down and to the right, where each of these thick traces here represents an individual trial. If we tried to decode these individual movements using smoothing, which is kind of like a Kalman filter, which is very commonly used, or dimensionality reduction methods like GPFA, you can see we can sort of decode what the monkey was doing. We get the direction approximately right, but the precise details aren't great. But if we first denoise the activity using LFADs, kind of a modern machine learning method. Sorry, first I should mention, we can quantify that to say how much of the variability of the monkey's hand velocity were we explaining, and it's about 70%. If we first denoise that instead using LFADs, and then use a very simple decoding approach like a linear regression or optimal linear estimation, we can now recover about 90% of what the monkey was doing. And you can see kind of the huge difference in these trajectories. They're much more kind of consistent and much more veridical. They must much more closely match what the monkey actually did. So what I want to tell you about is some recent work where we're, this is, I think, a step in the right direction. But what I showed you here is kind of a really artificial scenario where the monkey is just kind of doing this very kind of controlled task. It's constrained. He's always like starting from his hand in the same point and always kind of doing one of these movements. And that doesn't really reflect kind of how we really use our arms, and that's not how we expect somebody to really use a BCI. So here's an example of data collected from this guy named Joey O'Doherty when he was a postdoc in Flip Save's lab at UCSF, where he had his monkeys move in kind of this random target task where a target would pop up, the monkey would move and chase the target, and then another one would pop up. And the key point here is like the complexity of this data is very different than when you just have kind of a stereotype movements with the hand always starting in the same place. So dealing with that with machine learning is actually tricky. So I'll just mention that we've developed some newer versions of LFADs, which we're calling auto LFADs, which allow us to now apply it to unstructured data. So removes the requirement that the monkey is kind of doing the same kind of stereotype thing over and over again. And what we get from that are, if I can get the movie to play, are trajectories now. So we do this in a completely unsupervised fashion, and then look at the representations uncovered by the network and see that they have a really close correspondence with what the monkey was actually doing. So here we're looking at representations of the population's activity during different reaching movements. And what we see is that, I just colored them after the fact, and that there is a close correspondence between the angle that the monkey was reaching and what the network kind of uncovered from the population activity in an unsupervised way. So, without being able to go into detail, let's say we're getting to the point where we can handle data that is much more like real world movements and much more like what we expect people to be doing when they use a BCI. Okay, in my last bit of time here, I just want to mention kind of another challenge that frequently occurs in BCIs, which is that recordings are unstable. And so what we commonly find is that we might, if we're recording from an electrode array and recording some number of neurons, if we look at, on subsequent days, you see kind of neurons come in and out, they change their amplitudes. Like a neuron will appear and disappear. And so that's a tricky challenge for decoding, because we kind of train these decoders and expect the data going into them to be consistent over time. So, we're recording from the same neurons and we try to extract meaning from those neurons. But with unstable recordings, it's pretty challenging to think about how we can get stable decoding performance and thus stable BCIs. So I'll quickly tell you about some recent work we've been doing, which is nonlinear manifold alignment via dynamical systems, where let's just say you take the LFADS approach I mentioned before, and you train it on a day's worth of data, and you can extract these underlying manifold representations, and you can train a decoder to map from these manifold representations to what the subject was doing. The problem is, if you came back and you ran that same model on a different day when the activity has changed because of non-stationarities at the input, you're not going to get the same underlying manifold trajectories. And so what that means is if you try to decode, you're going to get a very poor estimate of the intended behavior. So what we can do instead, this is some work from Brianna Karpovitz and others in my lab, is what we're calling nonlinear manifold alignment via dynamical systems, where, so we have that issue where we take the data from a different day and run it through the model, and it gives us this wrong estimate of the underlying manifold. And we can use techniques from machine learning, like unsupervised manifold alignment, to train a network, we don't have to train the whole thing, but we can train we can train the network to find, basically recover these underlying representations that we had before. And we can do that in an unsupervised way, meaning we don't need to collect new calibration data where a subject is kind of, doing the same movements over and over again to learn this mapping. But then we can use the same decoder that we had before and recover the intended behavior. So just to show you kind of what that looks like, maybe for a subject making a bunch of different movements at movements to 8 targets, this is what the manifold representations look like on day 0. We come back on a different day and you see that they've kind of collapsed. But if we use this unsupervised alignment approach, the network is able to kind of learn without us telling it what to look for. It's able to learn to reproduce those original trajectories. And effectively what that means is we can take, a decoder that we learned on day 0, and we can do a much better job of keeping it stable over long time periods. So this is without having to collect new recalibration data for the decoder. So here's an example where, the decoder does quite well over, the first 40 days. Maybe there's an outlier here that we have to learn to deal with. But comparing to either a static decoder, which you see in gray, or some other kind of, really actually, pretty impressive manifold alignment techniques, this approach that we've developed, Nomad, is doing quite well. So, to kind of summarize my key takeaway here, it's really just, a better understanding of the brain. So using some of these new insights from systems neuroscience and combining that with modern machine learning can lead to higher performing and more robust BCIs. And before I leave everybody, I'm just going to do a couple shameless plugs. We've been working on some alternative machine learning methods that are great at pulling out these same representations, but they can do it much faster than we could do it with an approach like LFAD. So using architectures like transformers. This is work from a student in my lab, Joel Yee, who's now at Carnegie Mellon. We can get some kind of similar performance as we did with LFADs, but we can reduce the inference time pretty substantially. So if you want to run something in closed loop, the difference between 26 milliseconds and 4 milliseconds is a pretty big deal. So I'm pretty happy with the potential of doing the same thing, but with alternate architectures. I'll also mention, something that I think is really important, and something that I'm proud that we as academics can drive, is that we can, I think it's really important to robustly compare these types of methods. Not just LFADs or NDT or anything we're developing from my lab, but there's a lot of good stuff happening, and we really want other folks from the broader machine learning community to be able to pitch in. So we just recently released this work. Please check it out at neurallatents.github.io. Joey being another wonderful collaborator on this work, where we have standardized data sets, APIs, ways to evaluate your models, just to try to really bring kind of standardization and lower the barrier to entry for folks in the space. And I think this is the very last thing I wanted to mention. Is just very short format. So if you really want to hear more about what I think about BCIs, we just released this massive review between myself and Sliman Ben-Smeya at UChicago, who's just amazing, where we talk about BCIs, decoding, motor control. We talk about writing information into the brain. I'm really proud that we included some stuff on ethics. So I think as this work is really accelerating, we need to stop and carefully think about ethics, and so there's some resources there and references to point to, as well as some information on alternate interfaces and stuff like that. So final shameless plug, in 2022, I'm hoping we can recruit 2 more postdocs to our team, both for clinical intracortical BCI work that we'll be doing in my lab in collaboration with some neurologists and neurosurgeons at Emory, as well as for rodent work that we're doing to understand the brain and spinal mechanisms that generate muscle activity. So with that, I'll thank the amazing folks in my lab, my postdoc mentors and collaborators, ongoing collaborators, and support from various funding agencies. And thanks, everyone.
Woo. That was a fantastic talk, Chethan. Thank you for all of that. And yeah, anyone would be lucky to work with you, so people should definitely apply. There are a couple questions that I think are very quick, and maybe Chethan can answer them kind of in text afterwards, but I'll just start reading the ones that kind of would benefit from a verbal answer. So one anonymous attendee asked, do dimensions 1 and 2 in the neural dimensions correlate to orthogonal spatial directions of neural connectivity in the cortex? So I guess, can you connect these neural dimensions to like the physical hardware?
Yeah, I think that's a really great question. And honestly, I think that's a potentially a really exciting area right now, which is that most of the time when I and others talk about these like neural dimensions, it's really like an abstract description of neural activity, and we don't have a lot of good ways right now of tying it to kind of the anatomy and the connectivity and like what's really going on under the hood. So it's almost like an algorithmic or quantitative description of the activity without kind of a fundamental link to the biology, or I'm sure it's there, but I don't think we have good ways of addressing that right now. So at least I'm not the expert there, but I think it's a very exciting both question and potential avenue of research right now.
Great. So there's a question from Pavitra. She asks, what is a fair trade-off between additional computational time and performance? Ultimately, would these RNN models have to run in real time for decoding BCI control? And actually, I think Joey had a very similar question, which is how expensive is Nomad to run both learning and inference?
Yeah, great question. So, just to define a term exactly as Sergey used, and I think I used earlier, the idea of inference is if let's say you had neural activity, you've got a network that's already trained, how quickly could you, infer those underlying representations? So that would be inference with an already trained network. And so, we haven't done a ton of optimization in alpha, but it's, I think I pointed out about 26 milliseconds there. There are great ways of, there's a lot of ML research on kind of how do you run things at the edge. So like with lower compute costs and stuff like that I think could be applied. But, the tens of milliseconds, I think, is within striking range of what we want it to be, what we want things to be for a closed loop BCI. That being said, I also mentioned kind of this other work. So I think alternate architectures are really have a lot of potential there, like the neural data transformers, where we could reduce that by about a factor of 5. And so, yeah, you're absolutely right that real-time decoding to do that, inference times are critical. And I think Joey's question is a complementary one, is kind of this alignment procedure. So you have new neural data and you need to update your model so to mitigate kind of any non-stationarities. How expensive is it to run? So I would say right now, kind of on a GPU, it probably takes about 20 minutes to do. I think we're talking about expense in terms of time. In terms of cost, I don't know how much electrons cost, but some number. But yeah, again, this is kind of, we've mostly been focusing on sort of the getting it right rather than getting it fast. So I think there's a lot of ways to potentially speed that up.
Great. I think we have time for one more question, and then maybe you can answer the rest kind of in the chat box, which the question by Exon is, 1, how do you protect a Nomad against overfitting? And 2, how is this different from CCM used by Sarah Sola and Lee Miller?
Yeah, that's an astute observation. So just for some background, I think you might be referring to CCA, maybe canonical correlations analysis, which is what Sarah Soya and Lee Miller and Juan Gallego used for aligning manifolds across days. And I think that the critical difference is that that's a supervised method, meaning, if you want to kind of align the data from your new day, you kind of have to know what you have to collect a new calibration data set, meaning you have to stop use of the BCI and collect a calibration data set where you know exactly what the intention was while you collected that data, and then you can align. But if you're doing that anyway, you could probably also build a new decoder. So the key difference and the key challenge that we're trying to solve is how do you do that in an unsupervised way? Meaning, like without interrupting the use of the BCI, can you just kind of continually align to mitigate these potential non-stationaries? So in ML terms, I think that the big difference is what we call an unsupervised method versus a supervised method.
Great. Okay, so I think in the interest of time, we should move on to Joey. So thank you again, Chethan. And of course, people should feel free to email him or otherwise pester him with questions.
And thank you again
more of them.
Sergey.
Yeah, thanks. Okay, so now I'm very happy to introduce Dr. Joseph O'Doherty. He received a PhD in biomedical engineering from Duke University and did his postdoctoral training at the University of California, San Francisco. And his research has really focused on developing bidirectional brain-computer interfaces, meaning neuroprostheses sensorized by artificial tactile and proprioceptive signals. He was a co-recipient of the annual BCI Research Award in 2013 and the Ripple Promising Investigator Research Award in 2016. And then since 2017, he has been at Neuralink, where he is the brain-machine interface team lead. So thank you, Joey, for taking the time to join us today, and very excited to hear your talk.
All right, let's see, can people hear me okay?
Yep, we hear you loud and clear.
Are we good to go? All right, thank you for that really kind introduction, Sergey, and thank you to the organizers for the opportunity for me to speak to you today. My name is Joey O'Doherty. I'm a neural engineer at Neuralink, and the title of my talk is Fully Implanted 1024 Channel Brain Machine or Brain Computer Interface, subtitle Monkey Mind Pond with the N1 link. So I don't think I need to define my terms for this audience, but let's just start by, making sure we're all on the same page. What is a brain machine interface or brain computer interface? For us as a company, this is a device which records signals from the brain and in real time decodes those efferent signals to act on the outside world. BMIs may also contain a return path for afferent or sensory feedback from the world, which could be conveyed to the brain through patterns of stimulation. And Neuralink is developing such bidirectional BMIs. Although for this presentation, I'm going to focus on the efference that is outward signal path exclusively. What is Neuralink? I think also perhaps I don't need to define that for this audience, but just to say, we're a company founded in 2017 by Elon Musk, along with others, with the goal of developing high bandwidth brain machine interfaces. So our initial goal is to develop communication prosthesis intended to restore function for people with paralysis. An example of a similar BCI developed by the BrainGate Consortium is depicted on the panel on the right. And you can, in this particular example, a paralyzed study participant operated an instant messenger program using their brain activity and performed a variety of other tasks. Notice, however, though, there's a connector through which the neural signals are recorded, and it's visible on the participant's head. So we're working on bringing our technology and our device into the clinic and into the market, and this is going to take all of our focus over the next couple of years. However, after that, we think that the technology we're developing for this initial product may find uses in other medical applications and perhaps down the road, consumer devices. Okay, so let me just give you kind of like the high-level outline for like what we're going to be talking about today. Again, at a high level because of sort of a short amount of time. But our approach basically consists of four main thrusts. Thin film devices. These are basically the business end of our neural interface in the brain. Surgical robotics for inserting those devices. Custom high-density electronics and packaging, encapsulating basically our entire product, and then practical decoding, allowing this device to be useful to people, hopefully out in their daily lives. Okay, so we combine basically all of our sensors, our electronics, our packaging into a device that we call the N1 link. It consists of 1,024 electrodes that are distributed across 64 very flexible, ultra-thin probes that we call threads. You'll see why we call them that in a minute. Each of the threads contains 16 electrodes in our current design, although as you'll also see, we can fabricate these in a variety of shapes and sizes. The link samples neural activity from each of these recording sites, and it's capable of measuring both action potentials, that is spikes, as well as local field potentials. And it amplifies, digitizes, and transmits all these signals to the outside world in real time. So if we explode the link into its components, you can get a sense of how much it must accomplish in really quite a small package. It has to carry its own battery for power, an inductive coil for charging the battery, an antenna for communicating with the outside world, and along with that, all of the electronics which are necessary for amplifying, digitizing, conditioning these neural signals from our electrodes. And finally, it's encapsulated in a polymer enclosure, which protects these sensitive electronics from the rather challenging environment of the body. Zooming in first on the neural interface itself, these we call threads. These are really quite small, smaller than a human hair, which you can see in this image. And they can have many electrode contacts along their length. So these aren't just small, they're also very, very flexible and not stiff like typical electrodes tend to be. And it's our hypothesis that this mechanical compliance, both size and mechanical compliance, confers several advantages, including improved biocompatibility to the device. We make arrays of these threads using a photolithographic process. This allows us to rapidly iterate on our designs, customize our threads for specific applications or brain regions, and manufacture these devices at scale. If you zoom in on the threads, you can see that we have individual electrode contacts. These can be given surface treatments for lowering their impedance, for example, for recording or stimulation. You can also see, for example, reference electrodes. There's another prominent feature on the threads, which I want to highlight because this is an important part of our approach. We call these loops, and they're really crucial for the thread insertion process. So why is that? So the low bending stiffness of our threads makes direct insertion of the threads into the brain pretty much impossible. So we use the loops on our threads as a feature for grasping and manipulating each device. This is far too small to do by hand, so we use a tool, which we call the insertion needle. Let me just kind of go back to that so you can see it. Since these are so flexible, we need this needle to be very stiff. So we can decouple basically the stiffness of the needle, which we make from a tungsten rhodium alloy, from that of the flexibility of the threads. So basically make the inserter as stiff as possible and make the threads maybe as compliant as possible. The needle has some like features which are really too small even to see at the scale, but they allow it to reversibly, repeatably engage and disengage with the thread from the loop. And this is really an important part of our approach. Just to sort of like, elaborate on this point, you could perhaps do this by hand, but you perhaps wouldn't want to because it wouldn't be a scalable approach. So there are other devices like our threads, which have been inserted by shuttles by hand, but this isn't scalable. So we've developed surgical robotics to allow us to take this process and allow us to insert many hundred or thousand of these threads into the brain. And this allows us to, reliably and repeatably and precisely insert large numbers of them. We show a version of this robot called the R1 robot on the left-hand side of the screen. And you can see basically that robot with its like skin taken off on the right-hand side. I want you to focus in particular on sort of the business ends down here. This is the needle of the robot. And you can think of the robot as basically an array of actuators and sensors moving that around to where it should be to do its job. And notice in particular how there's a variety of optics on the robot that's kind of all focused on that one point. Okay, so it can be a little tricky to get an intuition for how the robot works and how the needle works and how the thread insertion, it's just sort of like a lot. So I want to kind of show you an example. This is a movie of a thread insertion into agarose, not into brain. This is a brain proxy. And what you're seeing is basically the business end of the robot descending from the top of the screen with a thread attached to it. It inserts each thread into the agarose and then it retracts, leaving the thread behind, and it just repeats this process over and over again. So I want to underscore a couple things here. One, this video is not sped up. This is actually in real time. All the insertions are occurring completely under robotic control. There's like a light show which is going on here. This has to do with the optics that the robot uses to both see where the thread is and see where it wants to insert the thread. And I also just want to point out that this example is actually from kind of an old version of the robot. And so there's some features on the inserter end, which are actually simplified and streamlined on the current version, but the principle of operation is basically the same. Okay, so that was how insertion into the brain could work. And now I'm going to show you an actual set of videos of insertion into a real brain. Now kind of showing what the thread threading process looks like. So how the robot actually picks up the thread. This is gonna, there's a lot going on here, and we'll just watch it a couple times. But there's a couple facts that are kind of useful to see. First of all, there's, again, this is a real-time video. You're going to see visualizations on the left of targeting. This is sort of where we want to insert the threads into the brain. And these are both pre-computed pre-surgically as well as intraoperatively by our robot operator and surgeon. And there's some false color imaging that tells the operator a little bit about the shape of the brain as well. And I'll elaborate on that in a minute. Also, we can place these targets kind of arbitrarily. This is really important because it allows us to avoid vasculature or other regions of the brain that we don't want to insert our electrodes into. And I'll tell you a little bit about that in a minute. Okay. So this video is here kind of to illustrate a couple of facts. One is that the brain is highly vascularized, and the second is that the brain moves. And it moves a lot during neurosurgery, sometimes quite a lot. It depends on the species. And this motion can be both due to heart rate, it can be due to respiration rate, but regardless of the cause, this complicates the process of placing electrodes precisely, that is with micron precision. And moreover, there's a challenge in that if you disrupt one of these blood vessels, that could be bad for a couple of reasons. It could be bad because you don't want to cause a stroke, one of the obvious reasons, but also it's possible that disruptions of the blood-brain barrier have some implications for the immune response to the neural interface. This is a hypothesis, but there's a lot of data that backs this up. So how does the R1 robot handle this brain motion? Okay, robotic insertion offers us a bunch of opportunities for neural interfacing that have not been available previously. It allows us to target very precisely, and it also allows us to plan our insertions to avoid vasculature. This is a stop motion video. On the left, you see a view of sequential insertions. This is sped up. And on the right, you see an OCT or optical coherence tomography view of each insertion site. This is a modality that permits the robot to track the surface of the brain and its motion, and it allows us to peer a short distance into the brain. So we can actually see blood vessels just below the surface, and we can actually also see the meninges as sort of layers on top of the brain. And we can use this to tell basically a little bit, peer into the brain a little bit about what some of the vasculature looks like, and also how it's moving in real time so we can avoid, especially the smaller blood vessels, which are perhaps not viewed on pre-surgical imaging. Okay, after we've placed our threads in the brain, what kind of signals can we record? On the left, you see a single thread in the orientation by which it would be inserted in the brain, so with the loop at the deepest site, and along its length are a number of yellow points, which are the electrodes. And now I've animated out a series of broadband traces that we can record simultaneously from each of these contacts. So this is a time series data point, and there's some sort of interesting features and structure in this data, but let's first focus on the data rate. So if we sample each channel at about 20 kilohertz, this is a very typical sampling rate, which is used for detecting spikes, and we represent them with 10 bits per sample. This means that each sample channel produces data at a rate of about 200 kilobits per second. There are 16 channels per thread, this specific example notwithstanding, and this implies about 3.2 megabits per second per thread. And as there are 64 threads per device, this means that there's over 200 megabits per second are needed to stream the full broadband bandwidth of the implant. So clearly we need to compress this data. Fortunately, there's a fairly straightforward solution, which involves detecting and sending only the features that we're interested in anyway, these action potentials or spikes. Now, a typical high bandwidth recording system could look like the following. So we record broadband data, we pipe it through a wired data link to a computer, and then we save this to disk for later processing. Probably a pretty beefy computer depending on the number of channels you're recording from. And so this is possible for wired data links, but it's completely infeasible for an implantable device. So we optimize the algorithms for processing our neural signals and for detecting spikes so they can fit within the power and compute budget of a custom ASIC that we call the N1 SoC. And this lets us take this neural data and compress it about 200 times and do it in about 900 nanoseconds, much faster than the time that it would even take for the brain to realize it happened. I'm not an electrical engineer, but I'll take you through a couple of the features of the chip that our chip team is working on. And some of the details of this have actually appeared in a conference in the 2021 proceedings of the VLSI circuits. So this has already appeared. So our chip is composed of 4 256 channel tiles. Each of them contains neural amplifiers with ADCs and a switch matrix that enables the user to dynamically set modes, for example, recording or stimulation or impedance, and change the referencing of our electrodes as well. There's a 16-core stimulation engine, which I'm not really going to talk about other than to say that it exists, but this is possibly could be useful for future neuromodulation applications that the company's interested in. We also have an impedance measurement circuit, which is really important to quantify the health of the electrode tissue interface. We have local power management, and finally, digital signal processing, including spike detection. just go over what the spike pipeline looks like at a high level. So basically, we sample our data at 20 kilohertz. After some gain and bandpass filtering, we remove low frequency oscillations and high frequency noise, compute channel statistics, which we can track using online algorithms, and then detect spikes using a custom spike feature detector, which is a little bit different than standard threshold detectors, but it allows us to be more robust to noise and artifacts than thresholding typically allows for. And finally, we take these spikes, we aggregate them to bins, we count them in vectors, and send them for doing useful things. So here's an example of real data recorded by the N1 link. So these are broadband signals which are sampled and bandpass filtered. And so you can see there's these events that ride on this, which are the spikes that we're interested in. This particular channel has actually very clear spikes and possibly a second one as well. And this is really apparent when you take your snippets and you overlap them so you can see the different shapes that are capable of recording. Finally, after that, you basically find the times that the spikes occurred, you put them into little buckets, and this gives you a time series that you can use for BMI. This is just one example, but here's a couple more, just showing that there's different shapes and sizes of spikes that we can detect, and that our spike detector doesn't have any free parameters which we're tuning to detect these, so it can operate entirely without user intervention, which is really important if you have a large number of channels. Okay, so can we do useful things with this? So we've implanted the N1 link in the hand and arm areas of several rhesus macaque monkeys. Probably this is also something I don't need to elaborate on too much for this audience, but just to say that monkeys are, a very standard preclinical model for BCIs because monkeys can use their hands and arms to interact with joysticks and other devices. And since our device is fully wireless, we don't have to rely on typical laboratory restraints. So the animal is free to move and behave in a naturalistic environment. Just also say, we are placing our device in motor cortex, which is an area that is involved in planning and executing movements. And this particular link is in the left motor cortex, i.e. controlling the right arm of this monkey named Pager. And he's acquiring targets using a cursor. And as you can see, this is a stand-in for a typing task. So we connect to the link using Bluetooth. Once it's connected, we can measure these vectors of bin spike counts that I was telling you about and model the relationship between these patterns of neural activity and movement direction as measured here by movements of the joystick. And then we could build a model or calibrate a decoder that is used to predict the speed and direction of upcoming or intended movements. So this is a cartoon of the game that Pager's playing. It basically consists of a grid of targets. This was pioneered by the Shenoy lab. But it's really nice because we can use this as a proxy for typing. So what we do basically is highlight one of the targets, which is the rewarded target. And then the monkey selects a target from an array of options. And this is analogous to really any communication task. And indeed, it's a really nice one because we can compute a bit rate or an information transfer rate that we can use to compare our performance with other options. Here's the equation on the right-hand side. I'll just unpack it very briefly to say that it has a numerator that depends on the log of the number of options. And we can subtract one to simulate basically making an error or hitting the backspace key. And then it also has a denominator that depends on the time that it takes. So we want the top part to be really big and the bottom part to be really small. You can think of a couple ways to boost or your performance, for example, increasing the number of targets. Although that doesn't really scale very well because of the log operator. Or you can also improve target accuracy, for example, only selecting correct targets and never missing, or perhaps reducing the amount of time to select a target by speeding up the transport phase of the movement, or selecting a target more rapidly if the cursor is over it, potentially using click signals. I just raised that to say that there's a bunch of practical things that you have to think about to design a high performance BCI. What kind of modulations are seen in Pager's brain? So here's a rather messy plot, but basically each circle represents an electrode and they're arranged in space as they are in Pager's brain. And there's a clear linear arrangement of the electrodes in each thread. So the size of the circle represents the modulation that we see, and the color represents the direction of that modulation around the unit circle. So if we take this arrangement of activities in space and overlay it on top of an image of the cortical surface during surgery, we can see where each of the threads penetrate the cortical surface. Just highlighting a couple things. One, notice again, we can place these wherever we want other than vasculature, not just in fixed grids. There's a slightly stronger tendency for tuning the size of the circle to be clustered in certain places. And this could be a consequence of the types of movements that pager is making. There could be actually quite a bit of information about different movements that are not represented in the joystick. I also want to, again, just point out, we can place these kind of in the appropriate places for the sorts of information that we want to measure. Okay, how do we decode all this information? So there are serious constraints placed on the compute, which is available to BCI in the kind of fully packaged device that we have. So this includes power, this includes heat dissipation, this includes memory usage. And a number of user criteria also have to be balanced. For example, in addition to raw performance or bit rate, it's also desirable that our models are very robust and stable, and that they're easy to learn, and that they don't they don't change over time in deleterious ways, and they should be useful for the user to do useful activities. So we can think of a couple of key principles that are important for practical decoding, such as using simple models that are very efficient to run, efficient and rapid to calibrate, and that can perform with reliable latency and low jitter. So I'll give you an example of an approach that we're taking. So we have our N1 device. It connects over Bluetooth and transmits these vectors of bin spikes in small bins. We take these bins, we do some temporal convolution on them and feed them into a fully connected network. And then these outputs are signals of interest, for example, VX, VY, and click. And these can be used to control devices directly. I'll just show a little bit. Again, this is a video maybe some of you have seen online, but it just shows a little bit of like the modulation that we see as pager's playing a game. So here, pager's playing Pong, a different game, and notice that the joystick is gone. So we're just showing a small number of the electrodes, of the activities of electrodes in his brain. So the top 100 electrodes with up and down preferred directions in blue and in red. Just notice that brighter colors indicate higher firing rates, and in the bottom trace, we have a yellow summary, basically, of the velocity that we're decoding from that signal. Finally, let's take another look at BMI control in a 2D typing task. Pager's holding the joystick in this example, but just please notice that it's unplugged. So we calibrate our decoders in monkeys using actual movements, but we won't be able to use such a strategy with people with paralysis. Fortunately, though, a lot of prior research has shown that neurons and motor cortex remain directionally tuned to movement, even in people with paralysis, and it's possible we can calibrate our decoder using strategies of imagined or intended movement. So after calibrating a decoder, the person will be able to, or would be able to type, compose emails, text messages, browse the web, and anything that you or I might wish to do with our computer, simply by thinking, how they want to move the cursor. I'll just close by saying that, I am privileged to speak with you today, but I'm really just representative of a large team of people, and also a technology which is built on decades and decades of research. While previous studies have used small numbers of electrodes to really achieve amazing things with connectors that pass through the skin, often there are technicians or caregivers that maybe are involved in connecting that BCI. And it's our mission to build safe and effective clinical BCI systems, which are wireless, fully implantable, that users can operate by themselves wherever they go, and that scale to large numbers of electrodes with robustness and information throughput rates that hopefully can really enable amazing things. And that recent engineering advances in the field and technologies are really what are paving the way for this kind of progress. I also want to just point out that if you have strong technical or engineering skills and you're interested in our mission, please do not hesitate to reach out and apply for one of our roles, because we have a great ambition and a relatively small number of people. So we could always use the help. Thank you so much for the opportunity to speak with you today.
That was awesome, Joey. Thank you. This is incredible progress. And yeah, sounds like a thrilling place to work for those interested. Our first question is highly upvoted, and I think actually great potentially for both of you, which is, what kind of progress, this is a question by Eric, what kind of progress and efforts do you most want to see from academic research to help inform your work, Joey, in industry, and vice versa? I guess if Chethan, if you want to answer as well, but maybe Joey first.
Sure. So, a lot of our focus, at least our initial focus, is on the device, the engineering itself, and the product. So making something useful, and that is reliable and not simply a demonstration. And so to that end, we're super excited for the academic world to discover new things about the brain and tell us about them. And then we are super excited to take advantage of those approaches to deliver, therapies and useful things to people. That said, we also, are interested in learning about the brain and hope that as we scale our devices, we can do some amounts of R&D ourselves too. But we really look and pay attention very closely to what the field is working on.
I guess maybe the vice versa question, by the way, fantastic talk, Joey. That's really amazing work. So, going the other way, kind of, I guess what I represent obviously a tiny portion of academia, so I'll just tell you my selfish interest. I think, obviously what you're demonstrating there is far beyond the capabilities of interfaces that are currently available in academia. And so, I think you can start to test with that type of interface, you can start to test a lot of questions that we just haven't been able to test. And there's certainly some pioneers in the academic space that are doing things like long-term recording during freely moving behavior and that sort of thing. But I think really a better understanding of the brain in those more naturalistic environments is going to be critical to real-world BCI use. And I think the types of technologies that you're developing are fundamental to answering those questions. So I'd love to see whether it's either in-house work or funneling the technology back to academia, like some inroads towards answering those questions.
Okay, our next question, I'm just going to go down the list, is from Alex. He says, neat talk. Joey, what is your thinking on scaling your craniotomy or durotomy? Have you at all noticed dural regrowth around your electrodes as they ascend to the N1 in any animals who have had the device explanted?
Yeah, really great question. So let me take it backwards. So have we noticed that the dura regrows? Yes, it does. There's a neomembrane which regrows when you penetrate the dura. But however, our approach is that we can decouple sort of fixed pieces, like the link itself sits in the skull flush from the threads, which are flexible and have tethers that allow it to not be tied to that skull mechanical linkage. As far as size of the craniotomy, and I think maybe you're alluding to targeting multiple brain areas and that kind of thing, that's certainly something we're interested in. And it really, there's a tension between size of that penetration into the skull and the sort of field of view of where you can place your electrodes and what you can see and target and so on, and also maybe the severity of the surgery or the length of the surgery or the recovery or the invasiveness. And so you want kind of like the best of both worlds, where you can put the electrodes wherever you want, but maybe have really tiny holes. And that's a very challenging problem, especially for robotic insertion. I'll just leave it at that.
That all makes a lot of sense. A question from Nikhil. Thanks for the talk. Is Bluetooth a bottleneck for this type of information transfer? What is the latency like?
Great question. Bluetooth is both amazing technology and awful at the same time. So first of all, it's a very small straw through which our data is going through. So we have to compress our data a lot. And if you think about scaling beyond our current channel count, it starts to be interesting to think about how you would do that. So that's one. But the flip side, of course, is everything is Bluetooth. So maybe you can imagine hooking up your BCI to your Xbox or your Tesla or something. So that's kind of exciting. The second thing, latency, it's actually BLE 5.2 is okay. There's something called a connection interval, which is basically how often you're allowed to send a message to your phone, mobile device, or a computer. This depends on the operating system and a lot of factors. But we can get our connection interval down to 15 milliseconds pretty easily, and 11 and a half with a little bit more work, and depending on your OS, down to 7.5 milliseconds. And there's other issues to do with reconnections and so retransmissions and so on, which get a little technical and complicated. But it's something where we know we need to pay attention to have a really high quality device.
Thanks, Joey. Another question from James. This is a question about next generation use cases. Have you looked into decoding speech directly from the language centers of the brain and coupling that with a voice synthesizer to help those speech impediments? I'm also very interested in this question.
So we have not, because we haven't found a really great animal model for speech, mammalian animal model for speech. So we haven't done that, but we do pay very close attention to what the field is working on there too.
Great. Okay, I'm going to ask, there's an anonymous question. Do you think that the hardware in the future commercial sort of non-clinical device will be largely similar to the existing hardware, or do you think major innovations are required to meet the expectations of a healthy customer?
Great question. I'll sort of answer that by giving our kind of like the approach that's in our corporate DNA, which is to constantly iterate and better our product. And to that end, that's obviously a challenge with a medical device because we have to have design controls, we have to lock down aspects of our device to test them, and we have to ship those tested devices. But I expect everything will be changing and improving continuously for this device and for later versions for treating different neurological disorders or even consumer applications. Everything is going to change and improve. So this is not the device that you're going to see the same one for years and years and years. In fact, what I've shown you is already a little bit obsolete already.
Maybe a very close question from Slava. What do you think would be the first popular non-medical application of a BCI?
I can say what I would personally find very exciting if it were possible to do, which is an imagination BCI. So something that lets me think, in 3D thoughts or whatever, and turn them into CAD. I think that would be amazing.
That would be very cool. Okay, Sam is asking if academia will be able to use these devices. I think you kind of basically answered that, saying we don't know yet. But if you have anything more to expand on, you're welcome to. Yeah, okay. Oliver is asking, what's the deepest the threads can go, and what are the biggest challenges in reaching deeper brain areas?
Yep, really, really great question. So why might you want to reach deeper brain areas? Different parts of the brain do different things, and there's a lot of deeper targets that are implicated in a variety of neurological disorders, Parkinson's being kind of an obvious one. I can answer by saying that we have designed the R1 robot to target any spot in the human brain, which is basically like 80 millimeters or something like that. Like it's quite deep. Now, of course, there are challenges to actually getting there, involving the length of your thread, the straightness of your insertion, avoiding vasculature, and so on and so forth. So our initial application is just in cortex for communication prosthesis, but we're thinking ahead to what it would take to do that safely.
Very cool. Okay, so I'm mindful that it is after 6. We still have more questions, so if you're willing to stay a little bit later and answer, that'd be great. But if you have another thing you have to go to, we can definitely end here, and thank you for your time. So what's your call, Joey and Chethan? Should we go 5 more minutes?
I'll drop off when Chethan wants to leave.
Oh, my kids are already asleep, so I could pretty much go for
all night.
Yeah, probably 5 to 10 is good.
Okay, there's a question from Yaya, which is, how stable is the decoding performance with the Neuralink interface from day to day? Do you need to do daily recalibration? Very relevant also to Chethan's talk.
Let's see, what can I say about that? No, we have an approach that allows us to not recalibrate every day. That obviously needs much more testing, but that we think is very promising. But to sort of answer that more broadly, that particular issue is something I think is very important for useful BCI. In other words, so I'm very interested in Chethan's and others' approaches here. How can we create a device that ideally the user calibrates once in their life and never again, and it just kind of works forever? If it has to recalibrate, it calibrates by itself. That's kind of our goal, and so we're working on strategies to do that, but it's a really hard problem.
There's a question from Yichen asking, would you consider using the threads to input information to the brain, especially given your past work in sensory write-in?
Yes.
Short
I'll
and
just
sweet.
maybe elaborate. I'll elaborate on that maybe perhaps by just saying a couple things. One, there's in the context of our clinical trial that we're gearing up for, there's additional risks involved in electrical stimulation of the brain. So we can, for our first application, think about disabling those features on our device, not using STIM. We have it on there. We'll use it later maybe, but we can disable it for safety purposes and splitting those concerns. But also from a technical perspective, stimulating through thin film electrodes is very challenging to the device itself. So we want to get a very localized current densities, and we want to do it in a way that keeps our threads lasting for a very long time. So this is something we have to pay really close attention to the material science, get our recipe right before sort of tackling that at scale.
Okay, and we have two kind of related questions, which I think are especially nice because they're related to trainee goals and kind of career. So one question is, do you recommend students interested in BCIs go into academia or industry at this point in the industry? And maybe a closely related question was whether Neuralink prefers specialists with deep specialized knowledge, for example, electrical engineering or signal processing, or more generalists with knowledge in many related areas like neuroscience, bioengineering, languages like MATLAB.
Do you want to take the first one, Chethan, or?
Oh, I actually thought they were both for you. Sorry.
Okay.
I think they're more both for Joey, but both can.
Sure. Okay. So
answer
let's see.
carefully.
Second one first. We are interested in people with deep technical first principles skills. So it kind of almost doesn't matter what your domain is. If like you have really good first principle skills and deep knowledge, and especially if you've shipped products, if you've like ever made something and send it out in the world, that's hard. So if you've done that, like we want to talk to you. With that said, if you're a T-shaped person that's both deep and broad, like okay, even more so. But that's a difficult set of skills to acquire. And I don't remember the first one. Do you want to just repeat it?
Oh, it was just, do you recommend students interested in BCIs should go into academia or industry?
Yeah, it depends what makes you happy, what you want to do. If you're interested in helping people, shipping a product, not necessarily running a research program of yourself, but working on a team, people working on a common goal, I found industry to be very rewarding. If you want to like tinker around and come up with theories and test them and kind of like choose your own destiny as a researcher, it's very difficult to get that kind of role in industry. That's you often have to be more.
I think your audio just cut out for a second. You have to be more blank. Okay, Joey's connection may be in and out.
Earbuds maybe.
Oh, classic. Yeah, battery life is always a problem. Well, given that
get that Neuralink implanted, Joey.
Exactly, we wouldn't have this problem. All right,
you can't hear him anymore, or
now we can.
Did any of the thing I said come through, or was I muted the whole time?
No, just the very last sentence was cut off.
I think I'll just high level, depends what you want to get out of life, really, whether industry or academia is for you.
I think that's great advice. Okay, well, we're already quite a bit over time. There are some more technical questions, Joe, if you want to look at them, but I think we should, call it a night and wrap up. I want to thank both Chethan and Joey for coming. I think we had well over 90, almost 100 attendees, and obviously this was hugely exciting to a wide range of audience. So thank you both for coming. And our plan is to keep doing these types of talks. We should have one next month, and there'll be a couple of months of talks that are more focused on sort of presenting data and progress by more junior trainees, and then back to this format. So keep an eye on the BCI Society website, and feel free to make suggestions. Thank you, everyone.
Thank you. Bye.